Okay, so we will look at SVM, support vector machine. We discussed as a principle during the lecture Tuesday. We will start by looking at MATLAB function SVM using the example the documentation provided. Go through these small examples. Then we will look at, again, the classification learner and accessing SVM algorithm using that interface. Then we will continue last week, the installation of Python. Last week we didn't make it run because the incompatibility between latest version of 3.12 Python you installed by default is not comparable with MATLAB current version 2003B. So what we have to do is to install a previous version of Python 3.11. So we will using this link to download and install Python. Then it should work. After that, once we set up Python correctly, we can start to look at this SC24 XCT. This is a package we developed in my lab. We only have Python version at this moment, so we really need to call Python to run this package. But we have this MATLAB interface, so you still don't have to leave from the interface. You can click, and the program will call Python environment. As long as you set it up correctly, you shouldn't have to learn Python to run it. Then we will look at some examples we used as a demonstration in the lecture. We will manually look at those interactions. At the end, we will install R because some of the package functions we will call from MATLAB R environment and get results back. There's a small program here. If you download and we will run it together. This is like a kernel transformation to show you how you make a 3D, 2D data points become 3D, make them separable. Okay. So let's start it with SVM. Okay. Questions? No? If you click the first link, that will lead you to support vector machines for binary classification. So this technical documentation is well written. Okay, it's better than a lot of the blogs, other professional writing. So those formulas. So we will move to the examples. We will move to train SVM classifiers using a Gaussian kernel. You can click this button. Let's see if I can open it. Yeah, this is a short demonstration. What we can do, I believe we can just copy the source code here in the gray box each time. So this suppose you can run within this page, but I suggest you just copy that and paste into the command line. The first blocks of the source code I put in here, okay? So this is some parameters and create a circle data, okay? Then we copy another block of code, paste into command line. So we have data 1, data 2. Each contains 100 data points. That's 2Ds. Then you copy this part using Ctrl+C and paste. That's the data we created. And then data 1, data 2, I believe data 1 is in blue, data 2 is in green. Data 1 in red, data 2 in blue. So this is 2D, the data you generate, the random generated. We should have exactly the same points. The reason is we set the same random number seed set to 1. So what you see on your screen should be the same as this one because they are not purely random. We start with the same seed number. Then I think here make another vector. So blue will be indicated as a -1, and blue will be red will be in +1. So this is just labels, create labels for so-called the class. If you look at the class, you have 100 -1, that's one class, and another 100 +1. So just binary labels. So this part is SVM classifiers using the comments, using this function. So you have data 3 is the class. The class is in the data, and data is in data 3 here. Data 3 should be the combine of the 1 and the 2, right? Yes, data 3 is 1 and 2 combined, and then you have a label. So data 3 is 200 data points, red and blue put together. And then you have a label, red in the -1, blue in the +1. So you gave this function called to fit the SVM, to train the SVM machine. So you gave the data and their corresponding label, binary labels. And you say, okay, I use kernel function to do the transformation before I set up this separation boundary. So this is the training step. After you finish this SVM machine, okay? So this becomes the classifier, and you are ready to classify new data. So we can copy and run this. So red are labeled at -1, blue are +1. And those circle ones are the support vectors has been found, identified by the model. Remember that you're based on the distance between points to this either is a line or a separate plane. This is another way to train it, but using different parameters. So you build another classifier, so called CL2. And you can use that to predict given the labels of new data, okay? Okay, let's look at this figure here. If I give this model a new data point, see the position I will give will be in here, for example, 1.5, negative 0.5. If I put a new data point here. So that's the model to predict what it is, belong to red or blue. So I hypothetic new data here, okay? 1.5, negative 0.5. This is data we want to test. So see a small x. So what we can do is to say predict using this trained model, and we have this. We should be able to give this 1.5, negative 0.5. So the predictor gave our the value 1. That should be the blue. Okay. Blue is 1. So if you select the point, say negative 0.5, 0, okay? If you try x2, so this is x1. If you try x2, 0.5, 0. if you use this as a new data point, you want to predict its classification membership, it should have -1, which belongs to red. Is that okay, everyone? So what the model is? The model is this one. You construct it using the training data. And then you test the new data. You can test both these two data points at the same time. So 1.5, -0.5, comma. Okay, you separate two input data points. And it will, first one will give you +1, second one will give -1. So it depends on how many input points you gave. And you can give 0, 0, and this will be, you can have a lot of inputs. The first model should be also all right. If you use the first model, remember we use two different parameters, settings to train the model, SVM. The first one, we call it CL, and second one, CL2. They produce the similar results. So you didn't see any kernel transformation because the information, the procedure has been embedded inside this function. It's doing this internally because you gave the kernel function what a type the kernel function is. So internally it's doing this, so you can separate the data points which non-linearly separable. So I'm going to try, if I don't give any instruction, so instead of doing this kernel, if I just ignore no kernel by default, I don't know whether the performance of this will be good enough. So if I use the model 3 without a kernel, looks like not very good. So at least the result is different from when you use kernel transformation within the training. Now what you can do is to, let's see whether, yeah, so if you open this, let me see where it is. Here, there's a m.m file, is a function. If you open this and copy everything, highlight and copy everything. And paste into command line. this small program bring up first an empty figure interface. Now you use your mouse, right click, regular click, and you put a lot of right circle. So this is just a collection of the random 2D points. And once you finish the center, then you click, right click to stop. And then you start to collect the blue points. And I put the blue points around. So this program will show you the kernel transformation operation to this. Once you finish, you just click right click and finished. And then the transformation will do this kernel Gaussian transformation, adding the z-axis to the data automatically for you. And you can say, okay, they are more separable than before. So that's what the kernel function internally is doing in the CVM function. Okay, just a small toy to play with. If you want to try that again, just copy and paste those code, and then start to click, and right click to stop collection of data, and then some new data. And then to look at the separation, okay? Do you have any questions? No? So I close this small program. I'm going to click the second link, number 2. So this will show you the SVM, but we are not going to use command line of this fit C CVM SVM. We just use interface of this classifier learner you used last week. Let's just copy this and make some example data. Okay. In here, I'm going to clear all. Just clean my workspace. Now I paste. So the classification problem now is to use variables within this table. So this table contains 35 different variables or feature variables. We're using those information to predict the label of the Y, okay? The Y is either G, B. This is a classification problem. So once we prepared this input data matrix and also the predict responsible variable, and we are ready to bring up this classification learner. You can follow the instruction on this web page. We start a session and then have to select the input variables and also the response variable y. Okay, we have to select what the input is. Should be this table, and then from workspace we want to select y as automatically. Yeah, we can use all the variables, I believe. Then we start the session. So from the model, we select we can select linear SVM. For example, I select a linear SVM. I get rid of a tree. We don't need a tree here. So I can combine, see what type of the classification algorithm I want to use. I certainly will use kernel. I just test this too. For this small program, I don't need a parallel, so I just uncheck this and run, train the model. So accuracy in the linear SVM is 100%. Well, this kernel version have lower accuracy. So that depends on the input data, whether they're linear, nonlinear combinations required. So this is like some kind of overkilled. So you bring more complicated algorithm, but you didn't achieve better results. So that's model 2, and that's model 3. Model 3 have quite a lot of this misclassification. Okay, so it really depends on your applications and what's your input, what's your variable you want to predict for. Yeah, hopefully you can find applications later once you have your matrix you want to predict or classify something. Always just set up your table and set up your vector you want to predict and train the model. So let's see if I believe this is the best model I can use for later. You can export your model and save it as a function. So next time you have new data points, you just predict. So this button allows you to export your model for later use. Okay, this will save into the workspace. Save to workspace. If you come back to here, you will see this trained model. Okay? Let's see how to use this. If I have this trained model, I can do dot prediction function. Let's see. I don't know how to use it. Let's try X first. 0. Yeah, but there's some kind of syntax you can use this model, but I don't know how exactly we can make it. Okay, the predict function, if I gave it the first data point, so this function I have to read the documentation and see how we can use this predict model, trained model.
If you go back to your workspace
Mm-hmm.
and then click on trained model.
Yeah.
And then click on how to predict. It's a variable on the bottom.
Okay. There's an instruction with built into this.
That's their instruction.
Yeah, that's good.
They included it as a variable.
Yeah. So that's what you can use. Yes. Good. Thank you. So let's see trained variable and how to use it. Print it out. How to predict. Yeah. So. So T is a table. Yeah, so that's what I try to use. So I try to use predict function to predict X, but maybe I have to put that into a table. I don't know. Shouldn't. But anyway, we can read the documentation and work it out. Okay. All right. So what's next? So I'm going to clear my workspace. Now we are going to spend some time to set up Python. And the Python, we set up 3.11 version by click this link here. So last week, we just clicked the first one and installed the latest version, but we need to back a little bit, just one previous version. If you click this rather than the top one, and then install this mini codon on just for yourself. Now let's change this to a place where you can find it later. So I will get rid of app data local because they are hidden folders. Systems folder you won't be able to see, but we'd better to install into some place that we can see where they are. So that's the place I would suggest you install it. In your machine, I don't know what it looks like, but that's your local root drive, and that's my username. Probably you have your own username, and I don't know whether on your system is the same. But anyway, you can install under your local folder, but you know where it is. Just remember this place. So that's where I'm going to install the Python system. That's it, I believe. Okay, my installation is done. I don't know on your machine. You after that you should have. If you type mini codon, you should have. You should have recently installed added anacodon mini codon 3 promote or PowerShell. Either of this should work. So I just confirm I installed the correct version. So here it shows my have a 3.11. Then we are ready to go. I need installation. So to get there, you click one of these black boxes here, okay? So I will work around and see whether you have that. So if you don't have a latest version installed, you have to rerun this quick installation to overwrite the older version. So from here, I will select the folder where I installed minicodon, and the Python should be in there, and you search for Python, okay? And you click this, say open. In that case, you should be able to have that already. Now, if you run this setup again, because you already pointed to the Python exe, so the program knows, okay, when I run Python code, I will use that part of the comment. That's all. If you decide to use another version, if you have a different version of Python installed in your machine, you can select another to point to the right one you want to use. But for now, you just use this because that's freshly installed.
So I should check the MATLAB version in MATLAB. Then
Yeah.
compatible.
Yeah. So yeah.
Might be different MATLAB.
You have a different version.
Yeah, version MATLAB in MATLAB.
Okay. Then you can use Python 10 or maybe 9. Yeah.
It's just this MATLAB.
This MATLAB, there's a table, and see in here, which lab. So if you have a 2023B MATLAB, you can use Python 3.9, 3.10, 3.11. That's all fine. If you have Python 3.8, you have to use MATLAB 2003A. So that's the table, yeah, comparable. Okay, come back to this interface. So I set it up already. And then we can import example data. I'm going to then we have to switch to 2D because the function I'm going to use only work on the 2D. So I switch this to 2D. Pick this. Okay, this 2D. And from external, I'm going to try to run this called data map plot. That's a Python package. I need a working folder, so I just use this. And yes. There are a lot of things going on behind the scenes. This function try to install that package in Python, and then going to give these data points, those cells, to the program that is run. We can take a break if you set it up, let it run. Come back in 5 minutes, you should have some output. Okay, now we will spend a little bit of time to install this package in Python. Okay. So I copied, I Googled this toolbox. This for this cell-cell interaction analysis. Then I will find this GitHub version. Well, let me see how to install this. Okay, let's do this. So we have to come back to this Python environment, okay, cordon, and a cordon, mini cordon interface. You know this. Let me make it bigger.
Different toolbar. Didn't finish. I think this is probably the first figure.
So here, let's see, I'm going to try. Yeah, please do this, okay? So I will, so this, give this, okay? In this environment, in this black box, you see conda install git. So we need a git to download that package. So I will put that in here, okay? Okay, so we will need to install a program called git in this black window. And once done, you copy this to install 24 XCT into Python, okay? That's what I'm going to copy, paste by right-click your mouse. Yeah, what I found, I need some click to help this program finish. Then if I do Python, and then if I do import single cell 10-fold XCT, so if I can confirm in Python, and if you can correctly import this package, then it indicates that your installation is done here, okay? We installed single cell 10-fold XCT in Python here. If you know how to run Python code, it's okay, so you can use Python to run this package. But what we are going to do is through the MATLAB interface. You don't have to bother yourself to run command line here. You don't have to learn Python. So here I just finish this part and close all the window. Because I already set up my Python environment and installed XCT, the program. The package, okay, I'm done. Now we can come back to the toolbox here, okay? We come back to toolbox. We are going to use manual annotation to look at this example I showed you in Tuesday's lecture. Let's see where the PowerPoint is. So the example I'm going to show you, we do have geo number, accession number, so I'm going to use that number. Okay, so this is a number. We are going to use this as example. So I copy this number to here, so we can take a look, okay? We can take a look of this particular sample we are going to use. It's a post-wounding day PWD12 single cell, and from mouse skin tissue. Okay, you have all the matrix barcoding and the gene information. So we just need this ID come back to here. We start toolbox, and then using import data and then a session number here, okay? And put the ID, you just remember, put that ID in, let the program to download and process the data for you, okay? Can you see this ID, GWS? So you need to put that in there, okay? 312.
Yeah, that's what I'm trying to ask. So you need to you download Python first, then you can install this toolbox, this cell interaction toolbox.
Yeah.
Without Python, you cannot just load the source code into the MATLAB.
Without Python, no, because this package is developed in Python. Yeah.
But if you need other packages, you can do the same thing?
Yeah, so you can, because a lot of Python package, you also just provide the expression matrix and the cell gene ID. Just let the package run and get back the results. Yeah. I'm sorry, yeah. Yeah. So there's one before here, right? Okay.
So you install the Git first. What's Git?
Well, this is not a small data set. It's quite So what I can do to accelerate the analysis, I will subsample, just use 50% of cells. Okay, I just make this program run a little bit faster than the real data. So I just do this subsampling. Okay, so I reduce the number of cells randomly, and then next, I will use this single-click solutions to get annotation of the cell types, mouse data. I just want to very quickly get some results to show before the end of this class.
Or you can just choose one sample instead of
One
sample.
This is one sample.
Oh, this is just one?
Just one sample.
Oh, I thought.
It's a huge, yeah.
Because usually you have several samples.
Mm-hmm. This is just one sample. They sequenced quite a lot of cells. Yeah, I found sometimes you need to click return. Yeah, just press.
I think it's about to finish.
Still, yeah,
This machine is really slow.
yeah,
It's better to remotely, connect
yeah.
the main computer.
Because you have so many computers running at the same
No,
time.
it's just
It's
just
just
like
this computer.
independent.
Oh.
This is depend on CPU, so yeah, it's not about network.
Maybe it's too big.
Yeah, not too big. It has so much dependency. So these all individually another package in order to run the manifold and SIM protocol. These all have to be installed already. So it's now getting the independent packages. So that's
Well,
why
this means you can algorithm
these are toolbox. Different toolbox. Yes, there's AMN
Yeah, some still running. Yeah, just have to wait. Yeah, just have to wait. Okay, good. Okay, good. The machine is powerful. Yeah, so now I can do something. I want to combine this hypothesized stellar cell with pancreatic because I don't want to sub into subclusters. So what I can do is to rename them. Okay, if you click this button here, I want to rename both of these stellate cells into just one cluster. I'm going to click this and say I want to rename cell type. Select hepatic stellate cell and rename it into stellate cell. Okay, then I click that again. I rename pancreatic stellate cells into stellate cell. Now I combine these two in just one name. Let's see, should I relabel cell type? Okay. And then I need the name of these two genes we test for. These two genes I used as an example. So those are the two genes. Okay. So I copy these two genes' name also, put in here. Okay, continue the draft. So this two gene name. So I need these two genes name. Come back to this interface here. I want to show the expression level of these two genes among those cells. That's my interface. So click this first button here. And then you know the name of genes, so you can just paste the name of those genes in here. Okay? This search will be case insensitive, so it's okay. So these two genes should be in there. Okay? So you click this tab to look at the different genes. So that's the picture I showed you in the PowerPoint slide. This particular one, so CAV1 highly expressed in this group here, in this group. So if we look at its annotation, this group is endothelium cell, right? This group. Stellate cells. Yeah, so this is very different from what I saw from the examples I use in the PowerPoint. So this group we annotate as a stellate cell, but this gene not expressed at all. So there's some misannotation in the examples here. So this group, remember in our plot here, stellate cells, but that particular gene we used in PowerPoint examples is not here. So this looks like a communication between this group of cell to fibroblasts, because the majority of those are the fibroblasts has been those ones, blue ones.
But you choose that cell type first, then you choose what gene expressed in that cell type. If not expressed in that cell type, you will not.
We should not choose this.
You shouldn't even see that gene in that
Yeah,
case.
yeah. So from this new annotation, it seems that I don't have the interaction between stellate cell with endothelium cell, so probably something else. Okay, but that's just the way you can annotate the cell, and we can if you have a good candidate, you want to compare, look at the different pairs. So just do this manually to check whether any of this makes sense to me, to you. So far, this pair doesn't make sense if you consider stellate cell with endothelium cell interactions. There's no expression of these receptor genes in here. Okay. All right, any questions? So this is part of this manual annotation. So I showed you this. Now we are going to run XCT to help us to detect some of those interactions. So I'm going to use examples between stellate cell and endothelium cell. Okay. This program will take long because you have to build gene regulatory network. So what I have to do, just ensure we will finish analysis before lunch. Okay. I will subsample genes. Now we have 13,000 genes. This is too much. I will use network and then remove some least informative genes to reduce the space. I probably will just select 2,000 genes, okay, to run this analysis as an example. But of course, you can use all the genes. Just take along, okay? The humans, so I select mouse gene, and then I will remove, for example, mitochondrial genes, a lot of ribosome gene, not important. I only keep genes with approved symbols, okay? Remove gene expressed too low, too high, then keep, let's keep 2,000 highly variable genes. Then you click this, I hope we can get rid of a lot of genes. Yeah, so we still have enough each cell type to run the program. Okay, do you need to let me to wait for 1 second, you finish? Okay. So now we are going to search the combinations between these 2,000 genes. We are going to use network and the cell-cell communication analysis here. We just set up. This program, yeah, I will first save this. Just in case I crash the machine. So CCI example, 2,000 genes. I just temporarily save this process data. In network, you can select cell-cell communication analysis. Then you are going to use documents. Use this as a working folder. Okay, a lot of the temporary files will be right in there. So overwriting, yes. Now, this is instruction, so some information about what it is, and you continue. You can still stop here, okay? And here shows you that Python, we already set it up. So just use this. Now you need to select cell type. You need to have 2 cell types. I will use stellate cell with endothelium cell. Okay, 2 cell types. If you want to change the idea, you can move cell spike. You keep 2 cell types in the right side. That's why you select it. Then when you are done, and this program will ask what direction you want to study. So now I believe what I will try to do is from endothelium cell secrete this ligand and give to stellate cell. So I select this direction. Then I just have to wait until the program gave me the back of the pairs of the ligand receptor pairs. So this is a time-consuming procedure. We invoked this parallel computing capacity, and you see here you should have all the green bars. That's a multiple core in the your CPU has been utilized at the same time. Just make this building of the gene regulatory network a little bit faster. We will build one network for endothelium cells and another network for stellate cells, and then this corresponding matrix build and until the end. The output of this will be ligand receptor pairs between these two cell types. You have a list which one is the strongest signal, and then you can check whether these pairs make sense to you, and you can search for database. Okay, other people have already found a relationship between them. Sometimes you found novel interactions. There's no previous report. Yes, for us, we just have to wait. Nothing else we can do.
You talked about in the lecture there's an interaction score.
Yeah, that will give you interaction scores. Yeah.
So after this.
After running, yes.
But you already free choose which cells interaction.
Yeah, you choose cell types to study interaction.
I thought you need to get interaction score first, then you look at which cells the interaction is high, then you.
Oh, you have to run this. For example, you choose cell type 1, 2, you make 2, 3, you make manually, and 3. Yeah, you do this at the end. You decide. Okay, you see. Okay, score is really high between 2 and 3. Then you have your. Yeah, you repeat this yourself. Yeah, on my machine is doing the second network construction. I think we can give this time. Now we can install R. Okay, in R installation is simple here. You just click ZenWorks and then search for RStudio and double click this. You should be able to install R. Oh, you got an error message. Well,
Because it was asking the admin permission access.
Oh.
For whatever reason, I don't know. I just click no, proceed, but at the end, I'm remotely connecting to the lab, so
Uh-huh.
maybe that's why this PC is maybe not.
I don't know. I don't know. Yeah. Yeah, same problem here maybe. Oh, yeah. Something wrong, but we saved the intermediate. The network has been built, so I will try to figure out what's wrong here and what's the next step. But in theory, you should get the results. Okay. I have to look at the error message here, and so what's
The result will be a table?
it will be a table, yeah. Yeah, so that's error message we get from the Python code, yeah. Yeah, there's something in there. It's not too hard to fix, but I should give it a try. Okay. So we cannot get the results today, but we have those temporarily saved those. So in theory, you shouldn't have to go back to the step one because all the matrix input data have been saved in this here. So we just have to make the Python code process those correctly, okay? You should have your R installed. So from here, if you click R Studio here, and you can check which version you have installed. So remember, you have a C program R 4.32 installed. Okay. So now come back to this interface. We are going to set up our environment. So don't worry about this, it will be fixed next time. We come back to this interface. In external, there set up our environment. So this program, you have to point to search for R script, exe file, which you have to know where you installed that. You say yes, and that's the place where I installed that. So I just select R script. So remember this program R 3.4.32 is in the bin, or you can use this as well, the same. But this one should work. Then you click OK. That should be done. Next time we will say set up R environment. It will tells you where the R executable file is. Then you just use this. And once you install that, those R-related functions should be able to run. If you click that, yeah, just give this try and to see whether we can run this program. So this program is called decontamination, because there are some of these reads content contaminations. This program try to detect those and try to remove. Then use this as a working folder, detect amber RNA contamination using this package. So now you are running R package to do the job and try to find contaminations in your cells. again, a lot of things going on behind the scenes. The program have to go to the website to download, install that package, and then put your input data, give to the R package to run and get back the R package results. Yeah, I think that's all for today, all right? And we have a spring break next week, and see you next week. Don't forget your homework, okay? Reading the paper. Yeah.
For those, if we do the RNA-seq data,
Mm-hmm.
the data, the FASTQ file we get from the VIBS school, the core.
Yeah.
So it's ready for me to just do alignment, right?
Yeah, you use.
I need to.
Yeah, yeah.
The same thing, we'll do alignment, right?
Yeah. Yeah, so there's some error message from our package as well. I don't know, so we have to fix that. Yeah, some package we don't know. It's something we cannot control. Yeah.
It's already installed in here. Yeah, the previous R version.
Already, yeah.
Maybe we just ignore the update. So the older R is working well in here.
Yeah.
4.21.
Yeah.
4.21 works better in. Yeah.
Maybe newer.
Yeah. So if you look at the suggestion here is under. Yeah. So you need a different version of R to make.
Yeah, it works.
Yeah. Okay.